Welcome back. This is section 7.4 notes, part 2. So we were just about to do our last example, number 3 on this page, which is the inverse tangent of 1. So I'm going to go ahead and draw my unit circle, and I'm going to think about where tangent is positive 1. That has to be at a location where my ordered pair is the same value for x and y. So that's going to be at pi over 4, and I know tangent is positive in the first quadrant and in the third quadrant. So those are my two possibilities. But if I jump back here and I look at the range of inverse tangent, remember that my answer has to live between negative pi over 2 and positive pi over 2. And I apologize, I actually have a mistake on this page. Shame on me. Grab your eraser here. These should not be less than or equal to. They should be just less than. Okay? So when we jump back here, and I use my green pen to draw the zone where tangent can live, these are going to be open circles, so not including my anchor points. And inverse tangent has to live in there. So almost the same as inverse sine. Notice these are very similar, except that inverse sine can include those anchor points, but inverse tangent cannot. Okay, so then the only answer that I can choose is this one, which is going to be pi over 4 or 45 degrees. All right, moving on here. We're going to do a little bit of calculator work just to make sure that we can do inverses on our calculator. So grab your calculator, and for each of these, you want to make sure that you are in radian mode to do these. All right, so you are just going to do on your calculator inverse sine of 0.13453, hit enter, and you should get 0.13494. Okay, number 2, try to type that in your calculator and see what happens. What you should discover is that your calculator should either give you a domain error or a syntax error, and that's because this is undefined. And the reason that this is undefined is because the value of cosine, or sine for that matter, cannot be bigger than 1. So cosine, sine cannot be greater than 1. Okay? If it is, it's automatically undefined. So that's easy. Okay, try your tangent of negative 3.5632. You should get negative 1.29719. And the last one, inverse cosine of negative 0.2378. You should get 1.81090. So just making sure that you're okay with the calculator function and being able to type this in and get the answers that match mine. Okay, moving on. We're going to talk a little bit about using exact values of expressions to find our answers here. Okay, so I don't have it on my page, but I believe on your page up here in the corner you probably have a little right triangle, which we're just going to draw in here, a 30, 60, 90 right triangle. So if this angle's 60, this angle's 30, right? And just remembering the sides of that triangle, that, you know, the base is 1, the hypotenuse is 2, and then the leg across from the 60-degree angle is square root of 3. Okay, so we're going to come back to that in a little while. Okay? All right, I want to make sure you have it on your page. Okay, so example number 1, we want to find these exact values. These are, first and foremost, PEMDAS problems. So you have to start on the inside and you have to work your way out. Okay, and I just want you to remember that when your inverse is on the inside, such as it is in our first example here, cosine inverse of 1/4, okay, you have to make sure that the input is in the domain of the inverse. Okay, so the question that we have to ask ourselves first is 1/4 in the domain of the inverse cosine? Well, let's jump back to our previous screen and take a look. Inverse cosine has a domain between -1 and +1. So for the particular problem that we're working on right now, 1/4 lives in that zone, so we are okay. All right, so what they're asking us is basically the inverse cosine of 1/4 and then the cosine of that. So in that situation, since 1/4 isn't a nice value on our unit circle, what we have to think about is inverse cosine of 1/4 is just going to give us a point somewhere in the first quadrant, right? Because that's where 1/4 would live as a radian measure. And then if we took the cosine of that, that's going to get us right back to the point where we started, which was 1/4. So in this particular situation, basically the cosine and the inverse cosine cancel each other out. Now I want you to be very careful. You cannot always do that. And we will see some situations where that doesn't work. Okay? Now let's take a look at example number 2. In example number 2, this technically has nothing to do with this one, so I don't want you to get confused. All right. The sine of negative pi over 3, well, I guess in some ways it does because it applies to that 30, 60, 90 triangle. But the sine of negative pi over 3, so if you think about where would negative pi over 3 be? Okay, that would be, I would be going clockwise. So negative pi over 3 would be in the 4th quadrant, right? And the sine of negative pi over 3 would be negative square root of 3 over 2. So what's inside here, the sine of negative pi over 3 is negative square root of 3 over 2. So now we're asking, well, what's the inverse sine of negative square root of 3 over 2? So where in the range of inverse sine is our y value negative square root of 3 over 2? And the answer is at negative pi over 3. So once again, this was a situation where the inverse sine and the sine cancel each other out. But I warn you again, it's not always going to be the case. We have to be careful. Now our next examples are a little bit different because this time our inverse is on the inside. So remember what I said, when the inverse is on the inside, you have to make sure that your input is in the domain of the inverse. We already know 1/2 lives between -1 and +1, so we're okay there. So let's start by looking at the inside. Just like PEMDAS, start on the inside, work your way out. Okay, so what is the inverse cosine of 1/2? That's asking us where on the unit circle that lives in the range of inverse cosine. Well, inverse cosine is from 0 to pi. Okay, so where from 0 to pi is the cosine value 1/2? And the answer is at pi over 3. So this part right here is pi over 3. So we're going to simplify this and say, well, this expression is now the sine of pi over 3. What is the sine value of pi over 3? Well, that is square root of 3 over 2. So that's going to be our final answer. Oh, I just noticed our 30, 60, 90 triangle is right here. Okay, how did I miss that? All right. Number 4, we've got tangent of inverse sine of square root of 3 over 2. So once again, start on the inside, work your way out. This is asking us, when we think about inverse sine lives between positive pi over 2 and negative pi over 2. So first quadrant, 4th quadrant. Where's the sine value? At what location is the sine value, or the y value, square root of 3 over 2? There's only one spot in the 1st and the 4th quadrant where that happens. That's at pi over 3. So then the question becomes, what is the tangent of pi over 3? Well, as we know, tangent is y divided by x. At pi over 3, the ordered pair is 1/2 square root of 3 over 2, right? So if I do square root of 3 over 2 divided by 1/2, that's going to be square root of 3 over 2 times 2 over 1. 2's cancel, and we end up with square root of 3. Hopefully you just have that memorized by now, that the tangent of pi over 3 is square root of 3. And again, that 30, 60, 90 triangle was there to remind you that we can always use a 30, 60, 90 triangle when we're talking about 30-degree or 60-degree angles, pi over 3 being a 60-degree angle, right? So we could have used the triangle for that as well. Okay. Next part here. We're going to evaluate our expressions by sketching a triangle. So if we start on the inverse sine of 3/5, okay? So we have to first imagine that we have our right angle here and we have some theta. So if the inverse sine is 3/5, then that means that the sine of theta is 3/5. Sine is opposite over hypotenuse, and hopefully we know that this is a Pythagorean triple. This is a 3, 4, 5 right triangle, but if you didn't know that, you could use the Pythagorean theorem to solve for that missing leg with a length of 4. So basically this question then becomes, what is the cosine of theta? Because cosine is on the outside, and the cosine of theta is going to be adjacent over hypotenuse, so the answer is 4/5. We're going to do the same thing here. We have a triangle with a right angle, and here's theta. It doesn't matter where you put theta. Okay, we're going to put it in this angle though. And so the cosine of theta is 12 over 13, and as we know, cosine is adjacent over hypotenuse. This is another Pythagorean triple. If you don't know, it's a 5, 12, 13, but you could certainly solve for that other side by using the Pythagorean theorem. So really this question becomes, what is the tangent of theta? Tangent is opposite over adjacent, so our answer is going to be 5 over 12. And then the last part of our notes here, we want to evaluate these expressions. Okay, so PEMDAS, PEMDAS, PEMDAS. Start on the inside, work our way out. So first, what is the inverse cosine of what half? 1/2. This is asking us what angle has a cosine of 1/2. Has to live in the range of inverse cosine. The range of inverse cosine is quadrants 1 and 2. So where is our x value 1/2 in quadrants 1 and 2? The answer is at pi over 3. All right, then the second part of it is going to be, what angle has a sine value of 1/2? And again, inverse sine lives in quadrants 1 and 4. So our answer has to be between positive pi over 2 and negative pi over 2. Where is the y value positive 1/2? That occurs at pi over 6. So this question really becomes, on the outside, what is the cosine of pi over 3 plus pi over 6? So if we make a common denominator, this is going to become the cosine of 2 pi over 6 plus 1 pi over 6, which is the cosine of 3 pi over 6, which is the cosine of pi over 2. So finally, what is the cosine of pi over 2? Pi over 2 is at the top of the circle. The cosine value is the x value. The answer is 0. And that's all.